Hello, welcome back. Lecture 59 today. If you recall, this week we are talking about on-wafer measurement. In the last lecture we discussed about the concept of de-embedding in general, and also about we introduced about the base of the small signal model, how the small signal model is built. Okay. So what we are going to do today is to understand the transition from the basic small signal model with just 3 parameters or 3 components to the actual small signal model of the device, and then we are going to talk about the de-embedding concept behind that. Okay. So over to the whiteboard here. So in the last slide, we saw that there are 3 components predominantly, the CGS and the output resistance and the GM-VGS in the small signal model, but in reality there are many components. So maybe it will be helpful if I sort of show the physical structure of a transistor. For the sake of simplicity, I will just say this is an L-GaN transistor. Okay. L-GaN transistor, and then there is a 2DG here. This is your source and this is your drain. This is going to be your gate. Okay. And of course this is the thing, and then there will be substrate. Okay, could be silicon carbide, etc. Now in the small signal model that you are building, okay, let me write down the small signal model also. So you had CGS from the last lecture, if you recall. Okay, this is your gate, this is your source, the entire source is source, and then you have the GM-VGS, and then you have the output resistance, correct, and then you have the drain here. Now remember, we should not forget that this model was actually invoked from the basic 2 port, the linearization of the nonlinear part, and invoking the I matrix and the Y matrix and the V matrix, remember V1, V2, etc. and Y111. We were basically using a mathematical model, and then we developed this small signal model from there. So it's forming from that point. Okay, it's not magically appearing out of anywhere. Now there are many things to consider here actually. So the first thing is that the gate and the source, of course we have already talked about the CGS. So there is the gate source coupling, CGS, but the gate also has a resistance. This resistance is in series, like the gate will not feed current into the channel, but there is a resistance that is provided by this L-GaN barrier. So this is the input resistance, you can say. So I am going to put maybe I can change the color here. Yep. So what I am going to do is that I am going to put an R in here. That R in is basically the input resistance from the gate towards the source. Okay, its value is pretty high in a generator. Okay, that is the input resistance. Now the same thing, the gate will also couple to the drain. So there will be a CGD. Okay, it's say the gate is symmetrically placed, just assume. Okay, so CGD is also going to be the capacitive coupling between the gate and the drain. So between the gate and between the drain, I will have a what I am calling you as the CGD, right, and there will also be a resistance between the gate and the drain. The gate and the drain through the L-GaN barrier, it's an insulating barrier, but there is a resistance nonetheless. I will call it RGD. Okay, so those are the 2 components, those are the 3 components that have come here. Okay, so that exists there. The gate might also leak, by the way. There may be shunt path. Okay, there may be dislocation, for instance, that are leaking. So there could be leakage through the gate to the source. There is a gate to source leakage, there is a gate to drain leakage. Those are shunt paths. Anytime you have a device, the shunt paths refer to the parallel leakage paths that might be there. Okay, so I have to include that as a leakage. So RLGS, I can say the gate to source leakage, and that's in shunt. So I have another here which is RLGD, that's the gate leakage to the drain. Okay, so those are the drain components that are there. Fine, I cannot help them, those has to be there. Now the gate metal has its own resistance, RG. Okay, the RG is a gate resistance, so that gate resistance will come here, RG, that gate resistance has come here. You cannot do anything about it, that resistance has to be there, the gate metal. Now the source has a contact resistance, and then the source in the 2DG has a source access resistance. I club them together and I call it the source access resistance, RS. So that will come here, right. Similarly, the drain has a contact resistance, the metal will contact the 2DG, that is a contact resistance, and there is a drain access resistance that we have talked about enormously. I will combine both of them and I will call it RD. So there will be a drain resistance here, RD, right. It has built the model very well now. You see, we have talked about most of the components here. Now there are a couple of more components that may not be always useful, but it is very important to by the way, this R naught sometimes people also call it G naught, it's basically 1 by R naught. Okay, just to make sure that you don't get confused by the nomenclature in some textbooks. Now the drain and the source, when you have depleted this in the off state, for instance, the source and the gate might source and the drain, sorry, might capacitively couple to each other. The source and the drain through the buffer might capacitively couple. So I have to give that, this is the drain and this is the source, right. So I have to couple that, so I have to give another capacitance called CDS, the drain source coupling capacitance through the buffer, and this is the this could be through the depleted area, and through the buffer there could be coupling. If the buffer is leaky, then this becomes a problem. Okay, so that's a drain to source capacitive coupling that's there. Now what are the other components that we are missing out here? I think we have built everything so far that is needed. So this there is an intrinsic device, then there is an active device. Okay, so maybe I can use a different color here. I'll use a black color. Okay, so the intrinsic device ended here. Okay, this is the intrinsic device. Can you see that? This is your intrinsic device. That is the true device, the real intrinsic device. Okay, and maybe I can use a different color again. Maybe I'll use a light blue color, or it's the same color. So maybe I can use a dark blue color here. Okay, so I'll talk. Then there is an active device. What is the active device? Active device encompasses the intrinsic device, and it also encompasses the gate resistance, because the gate resistance is there. That's a part of the active device. Okay, the gate resistance, sorry, actually the source resistance, actually the drain resistance was not a part of the intrinsic device. Sorry, the drain resistance will be encompassed by the active device. The intrinsic device, maybe I can change again, go back to the black color. The intrinsic device does not consider the drain excess resistance. It does not include this, does not include this, does not include this. That is the intrinsic device. The active device will include them. So the intrinsic device does not include the gate resistance, the source excess resistance, and the drain excess resistance, but when you include them, you call them the active device. Okay, so that is the active device. Fair enough. So we have now the gate resistance, the gate to source leakage, the gate to drain leakage resistance, the gate to drain coupling capacitance, the gate to drain resistance, okay, the gate to source resistance, the input resistance here, the GM-VGS, which is the output current ID, and the output conductance, and of course the drain source capacitance. Okay, so we have built that out. Now what remains, and maybe I can go to the next a proper thing here, is that I have built the gate. If it's basically an extension from the last slide. This is the RG, okay, and then I have RLGS, the leakage, in parallel with CGS and Rin, okay, and then I have the source resistance. This is the gate drain capacitance, this is the gate drain resistance, okay, and then I have GM-VGS, the current flow, then I have the output resistance, then I have the CDS, the drain source coupling capacitance. Okay, so I have brought it here, and then of course I have the drain resistance here, and then the drain there. Okay, of course I had a parallel connection of RLGD, the drain leakage. You can ignore, if the barrier is good, you can ignore that. There are a couple of more things, by the way. The source, and the drain, and then there is a gate. Remember, in a real device, this source and drain pads will be big when you have especially have coplanars and stuff like that. So those, because those are giant metallic pads, they will introduce some inductance. Okay, inductance. So what will happen is that there will be a gate inductance, there will be a source inductance, and then there will be a drain inductance. Sorry, LD. Then this is the drain, this is the source, this is the gate, and this is the source. Okay, so those are the inductances that are appearing because of these big metal pads. They have inductive behavior. Okay, they are in series with this everything. Now the pads will also couple these big pads. What I am talking, when I say big pads, I am talking about the CPW pads like that, right? This is the active device, for instance. Okay, I am talking about like that. These pads, these are the inductance, source inductance. This is the drain inductance. This is the source inductance again. So there are two source pads, source inductance. This is the drain inductance LD, and this is the gate inductance LG. Okay. However, there is a substrate parallel to this, so there will be coupling capacitively also to the substrate below. So that's parallel. So the gate will couple capacitively. So this is called C pad capacitance, this big pad will have a capacitive coupling to the below, this pad capacitance between gate and source, there will be a pad capacitance Cp between gate and drain, okay, and then there will be a forward coupling between the gate and the drain. So this gate, this is the drain and this is the gate, they might also couple capacitively through the substrate below. So there will be another big CPGD, the coupling between gate and drain pad between the gate and the, so this is the big small signal model that we have built, okay. Can you see where we have come from and where we have gotten into? The big pads are introducing these inductances and their big pads are also introducing parasitic coupling to the substrate which cannot be ignored, okay. So now if we look at the actual device schematic with the CPW, what I am going to say is that I have this source, active source, I have this drain, active device, and then I have this source, and of course I have the, for instance, the gate, okay, the gate is here, okay, this is the gate, and then this is this is the drain, there is no connection here, okay. All right, so okay, so this is the drain, correct, and then this is the source. I am not good at drawing, but just get the feel for this, okay. This will look, okay, this is the pads, okay, and your mesa, I will define it a red color maybe that helps you. The mesa active area is this only, okay, this is your mesa active area, okay, sorry, the gate will go all the way here, okay. So this is how it is. Now this is your source inductance, okay, this is your gate inductance, this is your drain inductance. Then you have capacitive coupling this, you have capacitive coupling this, okay, capacitive coupling this and capacitive coupling this. These are the pad capacitances that are coming in shunt, the inductances are coming in series, and of course you are going to couple them to the substrate also. So then how do I simplify it? Now I have to basically eliminate the effect of everything except though that is inside this red box, that is your active device. So everything else is a parasitic and you have, those are the pad parasitics. So that process is called de-embedding, okay. So now I have to de-embed the components or the contribution from all these parasitics. So how will you do that? How will I do that? So what I do is that this particular device that I showed you, this is the active region, by the way, the red colored shaded part here, that is the active region, okay, that is your active region, okay, that is your active region. Now what is going to happen is that you have these inductances in series, correct, you have these inductances in series, pad inductances in series, I am modeling everything together like that, and then the pad capacitances are in parallel, something like that, right. These are the inductor and this is the pad capacitors, okay, and of course you will have one capacitive coupling between the input and the output, I told you already, CPGD, okay, that is how it looks like. Now I have to basically build a model around it, okay, I have to build a model around it. The thing is, with higher and higher microwave frequencies, the parasitic effects become more prominent, so you cannot ignore them. So the pad inductances and the pad capacitances, the way they are coupling to the substrate and the coupling to each other, you need to subtract them, otherwise you cannot measure the true cutoff frequency, for instance. Just giving an example, whatever you measure, no, it will include the effect of all these pads also, so you have to de-embed them, you have to subtract them out. So what I do is that the active device, I will tell the active device has an impedance matrix of ZA. This is the impedance matrix of the active device. Look at this image carefully, okay, this image, I am going to build around that image. So I am saying that there is an active device with a Z parameter matrix of ZA, okay, the idea is to find this value of ZA, I mean this is the true device, I do not know what this will be, but I have this series inductances on the output Z2, I have series inductance on the input Z1, okay, and then I have to the source, of course this is the gate side, this is the drain side, and also on the source side I have Z3. These are the series inductances, basically they are feeding to my active device, the pads, the big pad inductances, you can think of that to some extent. And then I am going to have a parallel connection, and so this is gate. So the parallel has to be modeled by an admittance. So this Y1 is the gate pad coupling to whatever, and then there is this drain, there is a Z Y3 which is basically your drain pad capacitive coupling to the ground, okay. And then the gate drain might have its own Y2, which is your in shunt the capacitive coupling between the gate and the drain, okay, through the buffer. So this is your, I will call it, this is DUT. DUT stands for device under test, because what I am going to measure experimentally using a vector network analyzer or an instrument is the representation of this entire thing, and I need to find out ZA only. So what will I do? Okay. What will I do is that I will define some calibration structures on the wafer very close to, physically close, located close to this actual device. So this I am fabricating this on the actual wafer, no, this I am fabricating on the actual wafer. So I am going to fabricate some calibration structures, or I would say them de-embedding structures. I will have some specific de-embedding structures fabricated on the wafer very close to the device physically speaking, so that there is not much wafer or device variability. I do not want them to be far away in physically from the device. I will fabricate them close enough, and I am going to define two structures. I will call one of them as open structure, that is a different structure by the way, and I will call one of them as a short structure. Those are de-embedding structures that I will specifically design and fabricate on the wafer using microfabrication techniques, okay. So what I am going to do is that I am going to define an open structure from this CPW pad structures. I will make an open first. What is an open? An open is very easy to actually visualize. An open is like you are going to have the CPW pad, okay, the CPW pad, this big source pad, okay, and then you have the gate in a way, and maybe I am putting the gate on the other side, and then the drain, but there is no active device, there is no channel there. This entire area is mesa etched. That means this entire structure are sitting on the region where the active channel has been completely removed or etched away. They are sitting on the buffer, you can say, in a way, okay. So there is no active channel, there is no active channel in this part, there is no 2DG, there is no channel. So this is open, everything is open, they are not connected to each other. When you do not have the active channel, you do not have the series inductance coupling to the active channel from the gate side, from the drain side, from the source side, okay, you do not have the active device itself, then what will happen? This will go away. This will also go away because the pads do not have nothing to inductively contribute to the device, because the device itself is not there. But what will you have? What you will have is that these big pads will still couple capacitively to the ground, correct? They will capacitively couple to the ground. So you will retain this and retain this. So the open structure will look like you have the big pad capacitances Y1, Y2, okay. This is the drain side, this is the gate side, this is the source side, okay, and then you have Y2. So this structure, when you measure, when you bring your GSD probe tips like that and you are going to measure this structure, the open structure, you will measure S parameters, you can measure S parameter, whatever S parameter you get, no, that will correspond to this particular topology of the device. There is no active device here, okay. So just remember that. So what I am going to do, that the S parameter that I am measuring as open structure, I can convert that into Y parameter, Y open, because these are in shunt. So you can convert that into Y open. You can always convert S parameter to Y, Y to Z, Z to H. You can convert from anything to anything. There is a lookup table. You can run a C++ or a Python script or something. You can always, those equations are very standard. So you can convert the S parameter to Y parameter of the open, okay, that is great. Now if I measure the actual device, which is this, the entire device, you know, this device, okay, which I get basically this entire thing there, no. So if I do this device, I measure the S parameter and then I convert it into Y. So I call it Y DUT. So everything is there, the device, the open, everything is there, there is no difference. Now this particular matrix minus the Y open matrix, that I just described to you, okay, if you subtract this part from this actual DUT, then what is the circuit that you will get? You will get a circuit like Z1, okay, actually the ZA will come here, Z1, Z2, ZA and Z3, okay. This is what you will get, because the parallel pad components have been already subtracted out because of the open. Okay. So, if you do this, you will get this particular structure, but again this is a z parameter. So, you have to convert it in -1, that will give you the z parameter of this. Do you see my point? So, initially maybe I can what I can do is that create some white spaces here, 1 second. Okay. Okay. So, just to give you a feel again, this is Z1, this is Z2, which are feeding to the ZA, Z3, okay, and then you have Y1, Y2, Y3. This is your actual device with everything included, the as measured with all the pads and everything. Okay. The open is just Y1, Y2, Y3, gate and drain source. Okay. This is your open. So, you measure S parameter, you convert to Y. So, you get Y DUT, for here you get Y open. If you subtract Y DUT minus Y open and you take -1, that means you are converting it back to Z parameter. You take this and you subtract this from this, what you are going to get is basically Z1, Z2, ZA and Z3. Okay. You are going to get that. Alright, you are going to get that. This is the resultant you are going to get. But if you recall that I have, this is an open test structure, but I also have a short test structure. In a short test structure or a short de-embedding structure, I fabricate on the wafer a short structure. What I mean is that I have this GSG pads, and then I have this maybe the drain pad, and then I have this gate pad, okay, and I metallically short them all. This could be on top of the 2DG active channel, or this could be a channel, or this could be off mesa where the active channel is etched away. It does not matter because everything is metallic short. This is a short structure. Once you have the short structure, your network looks like this now, Z1, okay, Z2, your device is short, so that will no longer be there. This is Z3, okay. Of course, the pad will still be there, Y1, Y3 and Y2 will still be there, but the device is gone because it is shorted. So, this is the structure, the network that will look for Y. So, if you measure S parameter of the short and you convert to Y parameter, you will look like Y short, this like that. Now, what you do is that you subtract from Y short Y open. Remember Y open? Y open look like this. So, if you subtract Y open from Y short, correct, what you will remain is that Z1, Z2 and then Z3. This is all that will remain. This is what you will get, but this is Z parameter. So, you have to convert it back into -1. So, you will get the Z network like that. So, this quantity Y short minus Y open -1, which you are converting to Z basically, you subtract from this, which is Y DUT is the actual device that you are measuring, the entire with the pads and everything included, minus Y open -1. So, this is the Z parameter that corresponds to this, okay, Z1, Z2, ZA, Z3, and this the Z parameter, because I am doing -1, corresponds to this Z1, Z2, Z3. So, if you subtract them out and you have to basically, and this is your Z parameter, okay. So, you are subtracting Z and Z, then if you take an inverse of both of them, you are going to get Y of the device, or you are going to get Y of A, which was this part. Can you see that? You subtract that from that, you are going to get Y device. So, once you get Y device, you can convert it back into S parameter of from the Y parameter, that will give you S device, which means the true intrinsic device, or I will say the active device. You are talking about the active device, okay, and that from the S parameter you can find out FT, Fmax and a cutoff frequency, etc., because those S parameters will correspond to the true or the intrinsic or the, you can say, active device S parameter. You have de-embedded the effect of the open short, or using open short de-embedding or calibration structures, you have eliminated the effect of the pad parasitics, including the series inductances and the shunt capacitances. You have eliminated them and you got this S parameter of the true S parameter of the device, you can plot the S parameters. You can also convert to hybrid parameter H, you can plot gain, you can extract cutoff frequency, etc. Remember, for F max there is an equation, you have to just plot MSG, which is maximum signal gain, and MAG, which is maximum available gain, and they have this very nice beautiful expressions in terms of S parameter. These S parameters that you will use to plot this have to be this true device S parameter. You cannot use them from the as measured for the entire device, the DUT I mean, because that will include pad components, the pad parasitics. So that is why you are eliminating all these things, you are coming to the true device, okay, and you plot the MSG MAG for the true device, you find out F max. Similarly for FT, H parameter H21. So this is the main concept behind de-embedding, and you have de-embedded it to the plane of the device. The reference plane here has been the plane of the device, just outside or the active area of the device. You have eliminated all the pad components. Similarly for fixture or for packages also, when you do de-embedding, you need to use this concept. If you have a package for instance or a fixture, then you have to set up the reference plane, like this is the plane until which I am going to de-embed. Then you remove the active device or whatever package, and you do all the fixture wire bonds measurement, with this calibration structures are there, they are called cal kits, calibration kits. You can use them, open, short, true. There is also many other TRL, there is also true load, true line and reflect. There are many other calibration protocols also. Using them you can actually de-embed. There are many, this is just a simple explanation, but there are many variations of de-embedding. In fact, there are many approaches and techniques of de-embedding even on wafer, not to speak about fixture and package, okay. What we are using here is a short and open SO, but there is also more elaborate approaches of SOLT, short open load through. There is TRL, true reflect load. These are different techniques and approaches to de-embed on wafer, off wafer, etc., etc. Okay, we are not going to talk about that. That needs a proper course on RF characterization and on wafer and off wafer characterization, but that's okay. So this is the basic premise for de-embedding, okay, and this what we talked about is in the context typically for a compound semiconductor device for instance. However, when you go to CMOS or maybe an RF MOSFET, your ground you do not have like a necessarily like a coplanar, the ground will be automatically shorted to the substrate below, you do not have to have a via hole. And the problem, or I would not say problem, the thing in a CMOS like process is that you put it in a node like a 130 nanometer node or 90 nanometer node or whatever, you have a lot of layers of metallic connections, dielectrics, vias, etc. So you have a lot of layers of interconnects and metals, because it's in the node, it's a fairly complicated process, it's a much more detailed process. So all these different interconnects, all these different vias, they will add to parasitics also, okay, and with higher frequency it becomes worse. There is also the silicon substrate which is lossy, so it becomes worse with higher frequency, and the metal interconnects, the vias themselves will add significant parasitics. If you see, if you have carefully noted this de-embedding process that we talked about, it has assumed lumped parameters, this Z1, Z2, Y1, Y2, I have invoked lumped approximations, I have taken lumped parameters, and that is not accurate when you go to things like millimeter wave frequencies, okay. Millimeter wave frequencies, their distributed effects will become more prominent, more appropriate. You cannot have a lumped pad capacitance or inductance, it's not correct. You need to bring in the distributed nature, and so you need to avoid any circuit assumption on the pads or on the networks because of this lumped approximation. You need to invoke distributed. Now that becomes more complicated, okay. It will need you to have more precision standards and things like that, and especially for CMOS that becomes even more headache than compound semiconductor. So people have done, what people have done, they have done, people are smart of course, they have come up with approaches to de-embedding which does not depend on this lumped or the exact nature of the you can say the circuit or the network that you are using. What they have done is that they have done something called cascade based de-embedding, okay. This is a generalized cascade based de-embedding where you do not need to be worried about the exact configuration of the pads, and you do not have to make any assumptions on the lumped inductor capacitors just like we have done so far. Here you do not use open short for instance, you use something called through. What is through? Through is basically like a transmission line that connects from the input side or the gate to the output side to the drain, and not, it's not a metallic short between everything, it's just a through between the gate and the drain. You use a combination of these through lines which enables you to efficiently de-embed, okay, efficiently de-embed. And the question is that you don't, and the benefit is that you don't have to take any lumped pad approximation. No lump pad approximation is used. When you use this kind of a cascade based de-embedding using a through line, you don't need to invoke the lump pad approximation. You don't need to know exact calibration standards. This is really good. So what you do first is that, and if I talk about a CMOS like thing, for instance, I have a ground nevertheless pad, I have a ground pad, okay, and the ground pad is, you don't have to metallically connect to the active device because it's connected to the bottom of the, say LDMOS is connected to the bottom of the substrate. So it's like a default via hole, okay. So this is your ground, it's your ground, okay, this is your ground, and then you have the signal. So you have the signal which could be gate, the input signal, okay, this is the input signal, and this is the transmission line you are feeding the active device. So this is your active device, okay, this is your active device, the transistor, okay, this is your active device. The everything else, this is the transmission line, this is the transmission line, okay, this is your signal which could be your drain, for instance, okay. Although I did not place the active device symmetrically, you can assume that this is symmetrically placed just for sake of this, okay. So this is your and this entire thing will be on a metallic shield. In a CMOS process you will have many layers of intermetal dielectrics. So below that there could be a metal shield which is basically trying to shield the ground effects and things like that, okay. Now what I do is that I will define this as the plane of the device. Everything to the left is a left network, everything to the right is a right network, and that is the active device, okay. So I have the two port theory again, this is signal, this is ground, and signal means this is gate, okay. And I have all this thing, I will put it as a network, I will call it the L network. Then I have the device, the active device, I will call it device, and everything here is the right network, and then I have signal, then I have ground, this is the drain, the signal, okay, okay. This is the, I have basically not taken any pad approximations here, I am just putting everything together as a network, a left network and a right network. And here, although I will be measuring S parameter, I will not use Y or Z parameter, I will use ABCD parameter because it is cascade. So I am going to say that this matrix is an ABCD matrix, this is AL, and this is your AR, the matrix for AR. But what I am going to measure is I am going to measure everything together, I cannot separate them out, right. So if I am going to measure, if I am going to measure the S parameter of this entire thing and then I convert to I will call it DUT, this entire thing as DUT. So if I measure the S parameter of the DUT and I convert to ABCD parameter, I will call it ADUT, and ADUT is nothing but the left side network matrix, the matrix of the actual device which you are interested in finding out, and the right side matrix, okay. This is what we need to find out, but I do not know AL and AR. So this is how it looks like, right. Now what will I do? So what I am going to do is that I am going to use a special true structures. So the first I will use two true structures. So one true structure will be that I have this gate, okay, I have this gate, I am not gate, sorry, ground, this is the ground, this G is the ground, not gate, okay, this is ground, and then I have this also as the ground, I have this the ground here, right, and I have the signal, the gate may be here, sorry, the signal is S, and I will not have any active device, I will just connect it between the input and the output just like that. This is a signal, this is drain, this is your gate, correct. I do not have the active device, I just use a transmission line, this is a T line, the transmission line should be of the exact same width and metal thickness etc. as in the active device in the previous slide, okay. So I am using a transmission slide here, line here, and this is called a through, this is called a through. So I can measure the S parameter, I can bring a GSG pad probe tip here, 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 and I am going to measure the S parameter of this, I will call it a through, I will call it essentially what is happening is that this is the left side, this is the right side, I have no device in between, that is all it is happening. So I will call it the LR matrix. So essentially once I measure the L, this is a de-embedding structure LR, as I can convert it into ABCD parameter, so I will say it LR. So the ABCD matrix that I get from the measured S matrix ALR is nothing but the AL into AR. I get the product of both of them, correct. I get the product of both of them. Now this is the first de-embedding structure. The second de-embedding structure, I use the same thing. So I have a ground here, okay. I have a ground here, again I have a ground here, I have a ground here, and I use a through line again connecting the source signal to the signal. So this is drain and this is gate, of course, okay. Same thing that I had here, I had the L and I had the R. Now on the left side I am going to add this left side I am going to add this left. What I mean, I am going to add G here, I am going to add G here, and I am going to add S here. Same transmission line, the metal thickness, the width, everything same. So what is happening now here is that I am going to change the color so it becomes more visible, okay. If I define this, then this part is my L network, exact same dimensions I have used, okay, and this part is this. So when I measure this structure using GSG probes here and here, what I am going to get, once I get the S parameter I can convert to ABCD parameter. So I am going to get L, I will call it, this is L, this is R, right. So I will call it LLR. I am measuring this, this is very much measured from the S parameter. I can experimentally measure that. That is nothing but A into L, which is this, into A into LR, which is this, okay. So I can write AL as nothing but ALLR into ALR inverse, the inverse matrix. This is experimentally measured, this is also experimentally measured because this is here, this is measured. So if I have two measured matrices I can easily find out AL. Once I find out AL, I can find out AR by ALR into AL inverse. So I know AL now because of this, so I can compute the inverse matrix of that. I can multiply by this, which is also known because I have measured that, correct. So I can, and this is also known because I have extracted that. So if I multiply that I get AR. Once I get AR, I go back to the previous slide. What I do is that I take it on the other side. So AL inverse into A DUT into AR inverse is equal to A device. So I get, I will write it again here, AL inverse into A DUT, which is the measured, the actual, the device, essentially this device actual with all the pads, into AR minus this AL and AR I get from here, I already talked about. You take the inverse matrices, by the way, this will give you the ABCD matrix of the device. So this enables you to measure the true device matrix ABCD, and you can convert them into S parameter again back, Z parameter, Y parameter, whatever you need you can convert them back. This is a fantastic technique because this does not rely on any pad, lumped pad networks approximation, no lump pad approximation, and it gives you a very accurate device, the active device ABCD parameters, and from that you can find out the cutoff frequency in the actual S parameter, etc., etc. So that is called cascade based de-embedding that people use. Even in CMOS and RF MOSFET people use this. This is a very powerful technique. It does not rely on, because it basically encompasses everything as a network on the left, network on the right, okay. So what we are going to do is that we are going to end the lecture here today. We have talked about de-embedding in details, taking an example of a compound semiconductor device, and this is an RF MOSFET. This could be a compound semiconductor, very easily we can do this, but again it is easier said than done. You have to actually go into a characterization lab with a on-wafer device. You have to learn to use a vector network analyzer. We will talk about the vector network analyzer in the next lecture, and then you have to do these measurements. Calibration is very important. Without a very comprehensive and correct calibration, you will run into errors. So RF measurements are very complicated. Your calibration has to be really spot on, and once you do the calibration, then you measure the S parameter, then you do this de-embedding using all these matrices and everything. You need a script, a C++ or some kind of programming script to actually convert from S to Z, Z to A, B, C, D, etc., and then you extract out, and then you get the device parameters, and from there you plot actually. So it's a elaborate experience, and more you do the easier it becomes, of course, just like any other thing, okay. But here we are going to end this discussion. I hope we both learned a lot in this discussion about the S parameter and the de-embedding. So in the next lecture it seems like we will be running a little bit beyond 60 lectures because we have a few more things to cover. In the next lecture I am going to talk about calibration of a vector network analyzer very briefly, okay, that can be very elaborate by the way, and we are going to talk about on wafer measurements, some of the things like fixtures, package and things like that. Okay. So thank you for your time, I will see you next.